All right, guys, so 3.2, we're talking about the chain rule and using it in log functions and natural log and E functions. And I know we talked about this today in class. There was a lot of questions and a lot of conversations on the side about what we were all trying to wrap our heads around and understand. I wanted to just record a video going over the formulas and examples of using them without the confusion of answering a lot of different people's questions. So hopefully this helps clear things up a little bit. It may not answer all of your questions, but if nothing else, it's just a clear, concise video of rules, formulas, examples. So first things first, there are some old rules from Math 3 that are good to have in your notes when we're dealing with log functions. So the first one is if I have e raised to the natural log of c, the e and the natural log cancel each other out, and I'm just left with a c. Same thing if I have the natural log of e raised to the k, the natural log and the e cancel each other out, and I'm just left with the value k. If I have the natural log of two things being multiplied, I can split that up into the natural log of the first thing plus the natural log of the second thing added together, right? If I have two things being divided inside a natural log, I can split the top up and the bottom separately with a minus in between. I can take the top and minus the bottom, both of them with a natural log in front. If I have the natural log of x raised to the y power, I can rewrite that by putting the y in front and then doing the natural log of x. I didn't take the derivative and put the y in front. This is just a way that you can rewrite natural log functions. And in the homework, it might make some of the questions that you do a little bit easier by getting rid of the exponent. Two other simple rules that I need you to remember. The natural log of e is 1, and the natural log of 1 is 0. All right, so couple of formulas. I'm not going to go through the proofs. I'm just going to give you a formula, and I'm going to show you an example of using that formula. So the first formula that you've already seen is the derivative of e to the x is just e to the x. We did that in chapter 2. The derivative of e to the x is e to the x. But what if the x is not just an x? What if the x is some other function? Like, let's say that I wanted to take the derivative of e to the 3x squared. So instead of just an x up in top, I've got another function, 3x squared. Now, I have a formula that tells me what to do. Now, first things first, the chain rule is still the chain rule. I'm going to take the derivative of the outside, and I'm going to leave the inside the same, and then I'm going to multiply by the derivative of the inside. Some of these equations, some of these formulas that it gives you, look a little bit different because when you take the derivative of a natural log function, sometimes it's a mess. Taking the derivative of the outside can be a messy formula. So again, I'm not going to go through all the proofs of these formulas. I just want to show you how to use them. So the formula that it tells me to use, if I want to take the derivative of e to the u, and u represents some function like my 3x squared. That's kind of my u, right? These are the same thing. All it's saying is I'm taking the derivative of e when it's not just an x up top. What it wants me to do is e to the u multiplied by the derivative of whatever u is. And that's already the formula that we know. The derivative of the outside is e to the u. We've been doing that. It's just e to the 3x squared. That's the derivative of the outside and I just leave the inside alone. I don't mess with the 3x squared. And then I have to multiply by the derivative of the inside, which is that 3x squared part. And the derivative of 3x squared is just 6x. So e to the u prime, is just e to the 3x squared times 6x. So let's do one more example of that really quick. Let's say that I want to take the derivative of e to the 7x plus 5x squared. We'll make it even a little bit uglier. Now, to take the derivative of e raised to some exponent, my formula says it's e to the u. Well, there's my u right there. So I'm just going to rewrite it. E to the 7x plus 5x squared. That's the outside derivative. But then it wants me to multiply by the derivative of u, the derivative of this top part. So the derivative of that is what? 7 plus 10x. So my answer would be e to the 7x plus 5x squared multiplied by 7 plus 10x. I'm doing the derivative of the outside, leaving the inside the same, and then I multiply by the derivative of the inside. Okay? We also learned in the last chapter that the derivative of the natural log of x is 1 over x. So we're going to do the same thing today, but instead of just having an x right here, we're going to replace that with a function. So we're going to replace that with something like, I'm going to write this one down here below. I'll do it in red so it stands out. So instead of just taking the derivative of the natural log of x, I'm going to do something like the derivative of the natural log of sine of x. So inside my natural log is another function. And my formula is right here. The derivative of the natural log of some function is just 1 over that function multiplied by the derivative of that function. So my function on the inside is sine of x. So I just do 1 over sine of x. But then I have to multiply by the derivative of the inside, which is the cosine of x. So when I rewrite this, I end up with the cosine of x over the sine of x, which is this same formula that they give us right here. The derivative of the natural log of u is u prime over u. And mine, this turned out kind of cool. I don't know if I've ever done the derivative of a natural log with the sine inside, because cosine over sine, that's just, oh, where's my marker? That's just cotangent of x. So that's cool. The derivative of the natural log of sine is cotangent. All right. Maybe we'll do one more. Let's do one more that looks similar to that one. So let's do the derivative of the natural log of x cubed. Well, my formula, I'm going to use my formula right here, tells me that on top should be the derivative of u. Well, there's u right there. So on top is going to be 3x squared, because that's the derivative of u. On the bottom is just going to be the regular u, x cubed. And I'm done. 3x squared over x cubed. All right, next formula that you need to know how to use. Excuse me. If I want to take the derivative of a raised to the x, that's like taking the derivative of, instead of e to the x or x raised to the fourth, I'm doing something like the derivative of 6 raised to the x power. So x is my exponent, and the number, my base, isn't e. So the derivative of that, my formula tells me that the derivative of a to the x is a to the x multiplied by the natural log of a. Okay, we're not going to worry about why that's the formula. That's what the formula is. You take a to the x and you rewrite it, and then you multiply by the natural log of a. So my problem right here, the derivative of 6 to the x is just 6 to the x multiplied by the natural log of 6. Okay, the derivative of negative 8 to the x, I don't like using negatives, that might cause us some problems later. The derivative of 46.5 to the x power is just 46.5 to the x multiplied by the natural log of 46.5. Okay? Now, what happens if I don't just have an x up here? What happens if this value up here is not just an x? What if it's something else? So my formula tells me that if I take the derivative of a, some number, raised to a function, u, then my answer is a to the u, same thing I started with, but then I multiply it by u prime and by the natural log of a, which makes sense. This is the derivative of the outside part, and this right here in the middle is the derivative of the inside. So let's do an example. The derivative of 6 raised to the x cubed, which is weird to have an exponent in an exponent, right? Well, the derivative of that, my formula tells me that it's the same thing, 6x, 6 raised to the x cubed, multiplied by the derivative of the inside, the derivative of this, which is 3x squared, multiplied by the natural log of whatever a is, which in this case it was 6. Okay, another example, the derivative of 2 raised to the 3x. Well, my formula says to keep the same equation, 2 raised to the 3x, and then I'm going to multiply that by the derivative of the inside, the top up there, the 3x, which is just 3, and then I've got to multiply by the natural log of 2. So I get 2 to the 3x times 3 times the natural log of 2, and that right there would be my answer. There's not really much I can do to combine those things together because one's a natural log, one has an exponent, and one does not. So that's as far as I get. Okay, I've got some stuff here that I don't want here. Let's get rid, not that button. Let's get rid of this. Okay, log functions. We don't do derivatives of these very often, but it does happen. So if I had something like take the derivative of log base 7 x, and it wants me to take the derivative of that, it gives me a formula. It says 1 goes on top, on the bottom goes the x, and then I do the natural log of whatever a is, whatever this number is. So that number is 7. So I get 1 over x natural log of 7. I'm just plugging numbers into a formula, right? So the derivative of log base 19 of x would just be 1 over x natural log of 19. But of course, sometimes it's not just log base 7 of x. Sometimes it wants me to take the derivative of log base 7 with 6x to the 4th power up top. And I have a formula for that. It tells me that if this number right here is not just your regular x, we've got to do a little bit different formula. So it tells me that on top, I need to take the derivative of u, which is right here, which is right here. These three things go together, right? The derivative of u. So the derivative of 6x to the 4th is just 24x cubed. I drop the 4, times it by 6, and then I drop the x to a exponent of 3. And on the bottom, it wants me to put u. Okay, well, u is 6x to the 4th. And then I need the natural log of whatever a is, which happens to be 7. Okay, let's do one more after I get some of this stuff out of the way. I apologize, I didn't delete everything I needed to delete. Okay, so let's do the derivative of log base 2 raised to the cosine of x. All right, why not? Well, my formula, if this is not just an x, I've got to use this formula right here. And it tells me on top I need to take the derivative of whatever's inside, which is that cosine x. So on top, I'm going to get negative sine x. On the bottom, I just get cosine of x. And then I get the natural log of a, whatever a was, and in this case, it happens to be 2. And I could stop right here. There's no reason that I need to do more than I'm already doing. That right there is my answer. It does simplify. You can do some trig stuff to make it simplified, but that right there is going to be my answer. Okay, let's do the same examples that we did in class. Just with and guys, I appreciate your questions, and I'm glad that you asked them. I'm not recording this video because the questions bother me, but the questions do get us sidetracked, and I want to have the same information available without the conversations on the side. It'll be a quick recap of what we did, so maybe sitting at home, if you saw this, it's going to help you understand it a little bit better. So number 1 wants me to take the derivative of e raised to the x squared plus 3x. So I don't just have an x up here on top. I have an x squared plus 3x. And the formula for that told me that the derivative of e to the u is e to the u times u prime. So f prime of x is going to be e to the same thing, x squared plus 3x. But then I need to multiply by the derivative of this stuff for my chain rule. And the derivative of that is 2x plus 3. So e to the x squared plus 3x multiplied by 2x plus 3. Okay? Number 2, g of x equals the natural log of 3x. So instead of just taking the natural log of an x, I'm taking the natural log of a 3x. So my rule told me that if I take the derivative of the natural log of something, some function, then my answer is going to become u prime over u. So g prime of x is going to equal, u goes on the bottom. I'll do that first because that's really easy. U prime, the derivative of this u goes on top, which is just 3. And that's nice. The 3's cancel, and I'm left with 1 over x. So even though there was a 3 on the inside, my answer actually ends up being the same answer, as if the 3 wasn't even there. That's kind of cool. Let's look at number 4. Number 4 says y equals the natural log. And again, instead of just the natural log of x, I'm taking the natural log of t squared plus t. So my formula is going to be, this is my u, right? So my formula for y prime says to take the derivative of the inside, the u, and put that on top. So that's 2t plus 1. The bottom is just u by itself, which is t squared plus t. And that would be my answer. That is u prime over u, right? If my u was the t squared plus t. All right, number 5, the derivative of x multiplied by natural log of x. So I have an x getting multiplied by a natural log. And this is just a basic product rule. So h prime of x is going to equal the derivative of the first one, 1, multiplied by the second one, natural log of x, plus the derivative of the second one, well, that's 1 over x, multiplied by the first one, which is x. So if I rewrite this, I get natural log of x plus x over x, which becomes natural log of x plus 1, would be a good final answer. Okay, Number 6, g of t equals e raised to the negative 3 over t. All right, I'm going to rewrite this as e raised to the negative 3 t to the negative 1 because I don't like that quotient up in the exponent. So I'm just going to rewrite it and move the t up to the top and make it a negative 1. So the derivative of this, g prime of t, the formula told me to keep everything the same, right? It said to just take e and keep everything the same. But then I have to multiply by the derivative of this part, which is the derivative of this part. So I'm going to multiply by, I drop the negative 1 times negative 3 is 3. This becomes t to the negative 2. And I would be pretty happy with that answer right there. The derivative of the outside stays the same times the derivative of the inside. Okay, number 7, f of v equals 3 raised to the root of v. So again, I'm going to rewrite this. I'm going to rewrite this as 3v to the 1/2. So I'm taking the derivative, and I've got a base of 3 with some exponent on top that's another function. So this is kind of like I have a to the u. And my formula said the derivative of a to the u is a to the u times u prime times the natural log of a. So that means that f prime of v is going to be a to the u. That's just my normal function that I started with. So 3 root v multiplied by the derivative of v, or of u, sorry. The derivative of this red part up here. Well, the derivative of that is 1/2 v raised to the negative 1/2. But then I've got to multiply by the natural log of a, which is the natural log of 3. And again, I would stop right there. There's no reason to keep going, all right? All right, moving on. More examples. Example number 8 wants me to graph this absolute value function. Well, it wants me to graph the natural log of the absolute value of x. So if you graph that on your calculator, you're going to get this picture. And what it's saying is if y equals the natural log of the absolute value of x, then when I take y prime, I can ignore the absolute value signs. Y prime is just going to be 1 over x. It's not going to change my derivative. What it does change is normally I can't plug negatives into the natural log function. Like this right here doesn't exist. But because of that absolute value, I do have the left side of the function. But even though it's there, it doesn't change my derivative. So long story short, all of that is telling you that if you take the natural log of something, like this, natural log of the absolute value of 5 minus 2y cubed, you can just ignore those absolute values when you take the derivative. Some equations, we can't ignore the absolute values. Natural log functions, we can just ignore the absolute value. So, y prime, not y prime, because this is a function of y, it wants me to find the derivative of this. So the derivative formula tells me to take the derivative of the outside. Remember, this is kind of that natural log of u equals u prime over u. So my answer, on top I want the derivative of u prime. Well, here's my u. And the derivative of that is just negative 6y squared. And on the bottom, it just wants the regular u, which is 5 minus 2y cubed. So even though there was an absolute value there, I can ignore it and just take the derivative like I normally would, okay? All right, number 10. I think this is kind of where we left off in class, and it required us to start with something that you really haven't done very much. it gives us this function, y equals natural log of x multiplied by the square root of 2x plus 1 divided by x squared plus 1. If I tried to do the chain rule, I would have a chain rule on top of a chain rule on top of a chain rule. Not only that, I have a product rule on the top of a quotient rule. It's just going to become a really big, ugly mess. But I had you write down those rules at the beginning of class because when we're using natural logs, we can rewrite the function. So when I look at this natural log function, what I see is the function x getting multiplied by this function, square root 2x plus 1. And then both of those are getting divided by x squared plus 1. I like to see that because that means I can rewrite y. I can change y to equal the natural log of that blue part. And I can add the natural log of the red part. Because they're being multiplied together, I can add them together with natural logs. And because they're being divided by x squared plus 1, I can change that to minus the natural log of x squared plus 1. So I can rewrite this ugly product quotient multiple chain rule into a couple of different functions just being added and subtracted together, which makes them a lot easier to deal with. We can clean this up a little bit more. Natural log of x plus, I can take this square root right here, and instead of a square root, I can rewrite that as the power of 1/2, which is really nice with natural logs because the natural log rules tell me that if I have an exponent inside the natural log, I can move that to the front. So I'm going to put that 1/2 in front, and then I still have the natural log of 2x plus 1. That hasn't changed. That's still 2x plus 1. And then my minus natural log x squared plus 1, that's not going to change either. But now I have 3 different functions that are separated, and I can just take the derivative of each one. So y prime, now I'm going to take the derivative. The derivative of the first function is just 1 over x. Then I'm going to add the derivative of the second function. Let's see, there's a 1/2 in front. And then my formula, this is like a u right here, right? And my formula was u prime over u when I'm doing the natural log. So I'm going to put u prime on top, which is 2, and u on the bottom, which is 2x plus 1. So I just took the derivative of this part right here, and that's getting multiplied by 1/2. Then I'm going to subtract the derivative of this right here, which is also, this is kind of like having a u, right? So it's going to become u prime on top. So the derivative of that is 2x. And on the bottom is just the regular u, which is x squared plus 1. And I could stop right there if I was wanting to kind of clean this up and practice my algebra. These twos cancel. So I'm just left with plus 1 over 2x plus 1 minus 2x over x squared plus 1. And I think that's as much without finding a common denominator, which there's no way, I'm not doing that. That's plenty of simplifying for me. I don't want to find 3 different common denominators and multiply everything out, and it's just going to become messier. I like it the way that it is, okay? All right, number 11, we didn't get to in class, but let's go ahead and do it using the formula. The formula told me that if I take the derivative of log a of some function u, my answer, the derivative of that, was this function up here. We have it up here at the top, right? So it's this one that we highlighted in red. It's the u prime over u natural log of a. Okay, so we can go down here and we'll add that. It's going to become u prime over u natural log a. I'm not going to worry about where all those things came from. It's a formula. I'm going to use it. So my derivative, so the derivative of log base 2 of x squared plus 1 is going to equal u prime, which is the derivative of the inside, 2x. U goes on the bottom, so x squared plus 1. And then I need a natural log of a, which is just 2. So that's what my function, that's what my derivative looks like. That's my y prime. And then it wants me to plug in a 2. So let's do that. Let's take y prime of 2 is going to equal 2 times 2 over 2 squared plus 1 natural log of 2. That's going to become 4 over 5 natural log of 2. And you could stop right there. There is more simplifying that we can do. The natural log rules tell me that I can move that 5 up and make it an exponent of the 2. So I can rewrite this as 4 over natural log of 2 to the 5th power, which is just 4 over the natural log of what? 32? 2 times 2 times 2 times 2 times 2 is 32. So that would be my final answer there. Okay, hopefully that makes a little bit, it's the same stuff we talked about in class, but it's a little bit more concise, a little less interruptions, and that might give you a second time through seeing the same information. That might make some of it a little bit more clear. And I will see you in class next time.